As an example of uniformly accelerated motion, we're going to look at projectile motion. Projectile motion. This is two-dimensional motion under gravity, okay, or you can say curved paths under gravity, curved motion under gravity. Now we will look at the fact that gravitational motion is a uniformly accelerated motion before. In gravity, the velocity increases at a constant rate, and the direction of gravitational force is downward, and it doesn't have x component. So for gravity, the x component is 0, and the y component is negative 9.8 meters per second square, which is usually expressed by just g. Okay, so you can say that the acceleration for gravity is simply g in the j direction. It is 9.8 meters per second square in the negative j direction. Okay, so to get equations of projectile motion, all we're going to do is put ax equals 0 and ay equals tg in the equations of a uniformly accelerated motion. Okay, so first let me write the equations of a uniformly accelerated motion, and then we're going to specialize to projectile motion. Equations of a uniformly accelerated motion. We've written this equations in the previous section, but let me write them again. So we separate them into x motion and y motion, and this were vfx equals vix plus x comes to acceleration times time, and then we have delta x equals vixt plus half ax t squared, and then we have vfx squared equals vix squared plus 2ax delta x, and then we have delta x equals vix plus vfx over 2 times time. The same for the y component. We have vfy equals viy plus ayt, and then we have delta y equals viyt plus half ayt squared, and then vfy squared equals viy squared plus 2ay delta y, and then we have delta y equals viy plus vfy over 2 times time. Okay, so to get equations of gravitational motion, all we're going to do is replace ax by 0 and ay by g. So for equations of projectile motion, all we're going to do is put ax to 0 and ay to g. Okay, with that we get the following equations. This equation over here with ax equals 0 equals vfx equals vix. Okay, which means the x component of the velocity does not change because there is no acceleration along the x direction. Okay, and then if you apply that to the second equation, when ax equals 0, we just get delta x equals vix times t. So you've got delta x equals vix times t. That is the displacement just varies like a uniform motion, like speed times time. Okay, the x motion. Now we can do the same thing to these two equations, but we'll get the redundant equations. These are the two equations we have for this kind of motion. Now let's do that to the y equations. So you've got, we're going to replace ay by g, that's all. So you've got vfy equals viy plus gt, and then we've got delta y equals VIYT plus half GT squared, and then VFY squared equals VIY squared plus 2G delta Y, and then we've got delta Y equals VIY plus PFY over 2 times T. Okay, so these are the 6 equations we can use for projectile motion. Okay, so we have only 2 equations for the X motion, and then we have 4 equations for the accelerated motion. The X motion is a uniform motion, a motion with constant velocity, Vix over here, but this, the vertical motion, is an accelerated motion with gravitational acceleration, G, or negative 9.8 meters per second square. Okay, now let's look at a typical motion, projectile motion, to look at the variables. Suppose, let's say, an object is, maybe a bullet is fired from this height, let's say, this is the ground, and then let's say it's fired with this initial velocity over here. Okay, and then what's going to happen is we'll go up and then eventually we'll come back like this. Okay, all right, so just before it's the ground, we're gonna have a velocity over here. This is going to be the final velocity, and this is the initial velocity. Okay, now remember, the displacement vector is a vector whose tail is the initial point and whose head is the final point. So the displacement vector will just be this one, this vector over here. This vector over here is the displacement delta r. Okay, this is a vector whose tail is the initial point and whose head is the final point. Now you see the horizontal component of the displacement vector is delta x, so this is our delta x over here, and the vertical component, this one, is delta y. Okay, so delta x and delta y have nothing to do with the trajectory. They're simply the horizontal and vertical components of the displacement vector. So if you want to find out delta y and delta x, all it is, draw this vector from the starting point to the ending point, then the horizontal and vertical components will give you the delta x and delta y of the motion. Now the equations are written in terms of components, so let's look at the components. So for the velocity, we have these components. Okay, so this is Vix and this is Vfx, I mean Viy, I'm sorry, Viy. This is the y component, the initial velocity. This is the x component, the initial velocity. The same thing over here. This component is the x component, the final velocity, and this one over here is the y component of the final velocity. Okay, so these are the typical variables. We have the initial velocity and then the x component, the y component, and then we have the displacement vector and the x component, the y component, and we've got the final velocity and then the x component, the y component of the final velocity. So this is a typical motion that shows you how to interpret the variables. All right, so now let's look at some examples. Now let's say a bullet is fired from let's say 20-meter tall building, let's say horizontally, let's say with a speed of 100 meters per second. Okay, so that's what we have. This is what we have. We have the 20-meter tall building over here. This is 20 meters, and then it's being fired horizontally with a speed of 100 meters per second. Okay, so what's going to happen is, of course, we'll go fall somewhere over here. Okay, somewhere over here, and then of course we have the final velocity over here, we have vfx over here, we have vfy over here. Okay, and of course the displacement of the motion is going to be this vector over here, the vector connecting this vector over here will be delta r, and so this will be delta x, and this will be delta y. Okay, so let's write what we know. The magnitude of the initial velocity is 100 meters per second. How about the direction? The direction is east, so theta I equals 0. Okay, from this we can get the x and the y component. Vix equals vi cosine of theta I, which is 100 times cosine of 0, and that's 100. Okay, and viy is vi times the sine of theta I, that's 100 times the sine of 0 equals 0. What else do we know? We know this, delta y. But remember, the displacement is downward. Okay, so y is decreasing, so delta y should be negative. So we also know delta y is negative 20 meters. You see, it's displacement, a downward displacement, so it should be negative, which means y is decreasing. All right, now let's ask some questions. Okay, A, let's say calculate the time taken to hit the ground. Okay, so we're looking for the time from the initial point to the final point, from here to here. Okay, so we're going to select the suitable equation from this equations over here. Okay, if you look at this equation, we know viy, which is 0. We know delta y, so we can calculate time from here. Okay, so we're going to use that equation. That is, this is what we're looking for, and we're going to use the following equation. Delta y equals viyt plus half gt squared. Okay, so delta y is negative 20. It's a downward displacement. viy is 0. And then I'm going to use approximately negative 10 for gravity, but you always to use negative 9.8, and we've got t squared over here. Okay, so we've got negative 20 equals negative 5 t squared, and from that we get t equals 2 seconds. Okay, so the bullet will take 2 seconds to hit the ground. Now let's say calculate its velocity just before it hits the ground. Okay, so the variable we're looking for is vf. This we're looking for, the velocity just before it hits the ground. But remember, this velocity has two components. They are vfx in the I direction plus vfy in the j direction, so we have to calculate both of them. Okay, now calculating vfx is very easy because the velocity is a constant. Okay, so we have vfx equals vix, which we already calculated. It is 100 meters per second. So the x component velocity never changes. For vfy, we can use the following formula: viy plus gravitational acceleration times time. Okay, we just calculated viy to be 0, the y component of the initial velocity, this one over here. Okay, so this is 0, I'm going to use approximately -10 for gravity, and time is 2 seconds. Okay, so VFY is -20 meters per second. Okay, so now we have the velocity. The velocity VF is VFX in the I plus VFY in the J, and that is -100 in the I direction. Oh, not positive 100, positive 100 in the I direction, and then -20 in the J direction, this meters per second. Okay, so the horizontal component of the velocity doesn't change because there is no acceleration in the horizontal direction, and this is negative because just before it's the ground, the vertical component velocity is downward. Okay, it's negative because this velocity over here is downward, that's why it's negative. All right, now let's say how far horizontally did the bullet fall? Did the bullet, let's say, fall? Okay, so we're looking for delta x in this case. Okay, we're looking for this distance over here. All right, calculating delta x is easy because there is only one equation containing delta x, and that is delta x equals VIX times time. Okay, we already saw the initial the x component initial velocity is 100, and the time we calculate to be 2, so the bullet will fall 200 meters away. All right, let's look at another example. Let's say this time the bullet is fired from the ground. Let's say it's fired at an angle of 37 degrees over here, and let's say the velocity is 100 meters per second. So what's going to happen is we'll go up and come down like this. Okay, so let's write what we know. What we know is the initial speed, or the magnitude of the initial velocity, is 100 meters per second, and its direction is 37 degrees. Okay, so VIX, which is VI times cosine of theta I, is 100 times cosine of 37, and that's going to be about 0.8, that's going to be 80 meters per second, and VIY is going to be VI times the sine of theta I, that's going to be 100 times the sine of 37 degrees, and that is about 0.6, that's going to be 60 meters per second. So we have the initial velocity, the x and y components of the initial velocity. Okay, now let's ask some questions. A, let's say how high will it rise? How high will it rise? Okay, so we're looking for the maximum height over here. All right, so in this case, you see the problem determines what your final point is. So since being asked how high, this is our final point over here. Okay, and we're looking for this, for delta y. You see, this is our displacement over here, and how high is this one? So we're looking for delta y for this height over here. All right, so what we're looking for is delta y question mark, delta y question mark. All right, now let's see what we know the maximum point. Okay, the velocity is tangent to the trajectory. Okay, so the maximum height, the velocity is going to be horizontal. In other words, we know the direction of the velocity at the maximum point. its direction is 0 degrees because it's horizontal. Okay, so the direction 0 degrees, that means the vertical component 0. In other words, it's a horizontal vector, so it doesn't have a vertical component. So what we know is our final point, Vfy is 0. The vector is horizontal, it doesn't have vertical components. So what we know the maximum height is Vfy is 0. Okay, so now from this information we got to calculate delta y. I think the best equation to use would be this one. Vfy squared equals Viy squared plus 2g delta y. Okay, we're looking for delta y. Okay, so Vfy is 0, Viy is 60 squared, that's 60 plus 2 times negative 10 times delta y. Okay, so we take the other side, we get negative 3600 equals negative 20 divided by delta y, and we get delta y equals 180 meters. Okay, now B, let's say how long does it take to reach the maximum height? How long does it take to reach the maximum height? Okay, so we're still talking about the same final point. We want to find the time taken from the initial point to the maximum height. We want to calculate time from here to here. Okay, so we're looking for time to the maximum height over here. Okay, let's say this is T max. Maybe we can use this equation, Vfy equals Viy plus g times this time for maximum height. Okay, this is 0 at the maximum height, this is 60, the y component velocity of the initial velocity, and then this is about negative 10, and then we've got T max over here. Okay, time to reach the maximum height. So we've got negative 60 equals negative 10 times time required to reach the maximum height. So the time required to reach the maximum height is 6 seconds. Okay. Now let's look at this with this BC. Okay, C. Let's say how long does it take to return to the ground? Okay, so the motion is symmetric in this case. That is, time taken to reach the maximum height is the same as the time taken needed to go back to the ground, because the motion is symmetric with the same acceleration. So the time to go to the top is the same as the time taken to come to the bottom. So it's basically 2 times 6 seconds. It's going to be 12 seconds. But let's solve it using another way so that you have a good idea about the displacement. Okay, so now our final point is this point over here. Okay, so this is our displacement. You see, our displacement is a horizontal vector, so that means the vertical component of the displacement is 0. That's delta y equals 0. Okay, so what we know for this problem is delta y is 0. So delta y is 0. Okay, because the displacement vector is horizontal. So now we can use the following equation: delta y equals Viyt plus half gt squared. Okay, So the vertical component is 0. 0 equals, this one is 60, and this is half of negative 10 is negative 5 t squared. Okay, so we can take the other side. We get 6t equals 5t squared, and then we calculate, we divide by t, and we get t equals 60 divided by 5 for 12 seconds. Okay, so that's how you do it. But as I've said before, you know, the motion is symmetric. If you know the time taken to reach the maximum is 6, you can just multiply that by 2 and get 12 seconds. All right, and then now let's calculate its velocity just before it hits the ground. Okay, so now we're looking for this velocity over here. This is VF, and it has these components VFX and VFY. Okay, that's what we're looking for. Okay, so the question is calculate VF just before it's the ground. But remember, this vector has two components, so we can say VF equals VFX in the I direction plus VFY in the J direction. So we have to calculate both of them, okay? But we know that VFX equals VIX, which we have already calculated to be 80 meters per second, okay? And VFY we can calculate from VIY plus gravitational acceleration times time, okay? So the vertical component of the velocity, the initial velocity is 60, and then this one is negative 10, and the time we just calculate to be 12, right? So the 60 minus 120, that is negative 60 meters per second. Why is it negative? Because the vertical component of the velocity is downward, it's going downward. Okay, so we have the x component, we have the y component. So the velocity is 60 in the I direction minus 60 in the j direction. Okay, so we have this is meters per second, all right? All right. Oh, the x was 80. I was wondering whether they were equal. So the x is 80 meters per second, and so negative 60. This is the x component. All right. Now E, let's say how far did it fall? Horizontally? Okay, so in this case we're just looking for delta x question mark. Okay, and as I said before, there's only one formula for delta x, that is VIX times t. VIX is 80, the time is 12, so it's going to fall 960 meters away. Okay. Another example, let's say this time it's fired from, let's say, maybe a 20-meter building, okay, and it's fired with, again, 100 meters per second. Let's say this angle is 53 degrees, okay? So what's going to happen is it will go up and then it will come down like this, okay? That's what's going to happen. All right. Okay. Now let's say A. Let's start by calculating the velocity. Calculate its velocity just before it hits the ground. Okay, so that's what we want to find. This velocity just before the ground, maybe something like this. Okay, so it has x component vfx and y component vfy. Okay, so we're looking for this vector over here. V final is question mark. Okay, and V final is vfx in the I direction plus vfy in the j direction. Okay, so we have to calculate both vfx and vfy. Now vfx is the same thing as vix. Okay, so we know vi, the speed, times cosine of theta I. Okay, as you see from here, our initial speed is 100, our angle is 0. So, no, 0, 53 degrees, 53 degrees. Okay, so this would be 100 times cosine of 53, which is going to be 60 meters per second. Okay, how about vfy? I think we can use the following formula. vfy squared equals viy squared plus 2g delta y. Okay, so we know viy because viy is vi times the sine of theta I, that is 100 times the sine of 53 degrees, which turns out to be 80 meters per second, and delta y, we know delta y is the horizontal component of the displacement vector. This is a displacement vector over here. Okay, and this is its vertical component, which is 20 down, which means negative 20. Okay, and it's of course the horizontal component. All right, so delta y is negative 20 meters. All right, so now we have the following: vfy squared equals viy, which is 80 squared plus 2 times negative 10 times negative 20. Okay, so we've got 6400 plus 400, and that is 6800. Okay, so vfy mathematically is plus or minus the square root of 6800. Okay, but we know the direction of the vertical component velocity by the time it's the ground is going downwards, so we have to pick the negative sign. So we have to pick the negative sign, and this is 10 times square root of 68. This is 4 times 17, I think. So it's going to be negative 20 square root of 17 meters per second. Okay, so that is the horizontal component velocity. So now we have both the x component and the y component. This is the x component 60 and this is the y component. So the velocity is vfx, which is the x component is 60. So we have 60 in the I, 60 in the I, and then minus 20 square root of 17 in the j meters per second. Okay, so both the x component and the y component of the velocity just before it hits the ground. All right, now let's calculate the time taken to hit the ground. B, calculate the time taken to hit the ground. Okay, so looking for the time. Maybe we can use VFY equals VIY plus GT. So we have VFY is this one over here, negative 20 square root of 17, which is approximately equal to 4. So it's approximately negative 80. And VIY is 80, okay, minus 10t. All right. So we take this to the other side. We get t equals 20 square root of 17 plus 80 divided by 10. Okay. You take the zeros, it's basically 2 root 17 plus 8. This is approximately 4, so it's approximately 16. This is approximately 16 seconds is the time taken to hit the ground. Okay. Now see, let's say calculate the magnitude and direction of its displacement vector just before it hits the ground. Okay, so first we have to find the displacement vector. It is delta x in the I plus delta y in the j. Okay, so this is a vector we're looking at. This is a vector we're looking at over here. This is a vector delta r. Okay, so looking for the magnitude, which means the length over here, and the direction. You see this angle over here is the direction, but we're going to measure it from here, so it's going to be this angle over here. Or if you come this way and negative, it will be this way. Okay, when it's a negative angle, it will be this way. If you measure a positive angle, it will be all the way from here. Okay, 270 plus this angle over here. But we have to find delta y and delta x first. Delta y, we already know this one is negative 20. Okay, so we just have to calculate delta x first. Okay, so delta y is negative 20. So far we have this one, delta r equals delta x in the I minus 20 in the j. Okay, and delta x is Vix times t. Okay, cosine 53, and we've seen this is 60, and the time is, we said, about 16. So this is 60. What was the x component? The x component was I think Vi was 80. I think was 60. All right. So 60, and this is approximately 16. Okay, so it's 960 over here. All right. So we have the following: delta r equals 960 in the I direction minus 20 in the j direction. Okay. So but we'll be asking for the magnitude and for direction. Okay. So the magnitude would be square root of 960 squared plus negative 20 squared. Okay. The direction would be tan inverse of delta y is negative 20. Okay. And this one is 960. Okay. So this will give us a negative angle. Okay. All right, so these are the magnitude and the direction of the displacement vector. All right. Next, we're going to look at another kind of two-dimensional motion, which is circular motion. Okay, so let's look at circular motion. Now we're going to look at another kind of two-dimensional motion, which is circular motion. Circular motion. Obviously, circular motion is motion in a circular path, but first we're going to look at a special kind of motion called uniform circular motion. Uniform circular motion. This is circular motion with a constant speed. This is circular motion with a constant speed. So let's get the circular trajectory. Let's say of radius r. If the speed is a constant, of course the direction will keep changing, but if the magnitude of the velocity or the speed is a constant throughout the trajectory, the motion is called the uniform circular motion. So we're going to start defining some terms used commonly with circular motion. The first one is period. We're going to use capital T to represent it. Period is time taken for one complete revolution. This is time taken for one complete revolution. Okay, so obviously the unit is second. Okay, it's time. Second. All right. So let's say if it takes time t for n revolutions, if it takes time t for n revolutions, then we can calculate period at the ratio between the time and the number of revolutions. Okay. The next term is frequency. Frequency, we're going to use F to represent it. This is the number of revolutions or cycles executed per second. This is number of revolutions, or we can say cycles executed per second. Executed per second. Okay. Now, if it takes time t for n revolutions, so frequency will be calculated as the number of revolutions divided by the time taken. Okay. So as you can see from these two equations, period and frequency are inverse of each other. So we have frequency is equal to 1 over period. All right. So as you can see from here, the unit of frequency is obviously 1 over second. So the unit is 1 over second, and that's defined to be hertz, abbreviated by Hz, after the German scientist who produced electromagnetic waves for the first time. Okay. So the unit of frequency is hertz, and frequency is number of cycles executed per second. And then the next term in common use with this kind of motion is angular speed or angular frequency. We're going to use the Greek letter omega to represent it. Okay, this is number of radians executed per second. This is number of radians executed per second. Number of radians executed per second. Now there are 2 pi radians in one revolution. So the frequency f, in 1 second there are f revolution. So the number of radians per revolution would be 2 pi times f per second. So we can say angular frequency equals 2 pi times frequency. And since frequency is 1 over period, we can say this is 2 pi over period. Okay, so angular speed or angular frequency is number of radians executed per second. And since there are 2 pi radians in one revolution, we can say that angular frequency is equal to 2 pi times frequency, or 2 pi divided by the period. So obviously the unit for this one is radians per second, radian per second. All right. Now we're going to look at the relationship between speed and period. Relationship between speed and period. So remember, in this case we're dealing with a case where the speed is a constant. So since the speed is a constant, we can just say speed, we're going to use v for speed. Okay, we're going to use v for speed. Speed equals distance divided by time, right? But if we take our distance to be 1 revolution or 1 circumference, the distance is 2 pi r, where are the radius, and the time taken for a revolution is the period. Okay, so this is the relationship between speed and the period, is 2 pi times radius or circumference divided by the period. For example, let's say an object is revolving in a circle, let's say of radius 2 meters, let's say with a speed of 4 meters per second. Okay, so let's ask some questions. So we have the following situation. The circular path over here, the radius is 4 meters, and the speed with which it's revolving is 2 meters per second. So let's say A, how long does it take to make 1 complete revolution? Okay, so in this case we're looking for the period. Okay, period, question mark. What we know is the speed is 2 meters per second and the radius is 4 meters. Okay, so we're going to use the relationship between speed and period, which is 2 pi r divided by the period, or this implies period equals 2 pi r circumference divided by the speed. Okay, so using this formula, 2 pi times the radius 4 divided by the speed. So we get 2 goes away, 4 pi meter seconds. Okay, so this is the time taken for one revolution. B, let's say how many cycles or revolutions, how many cycles does it execute per second? Does it execute per second? Okay, so in this case we're looking for frequency, so we're looking for this one, and we know that frequency is the inverse of the period. Frequency is 1 over period, and we just calculate the period to be 4 pi, so it will be 1 over 4 pi, and the unit is hertz. Okay, let's say calculate its angular speed, calculate its angular speed. Okay, so we're looking for omega over here, and omega is 2 pi times frequency. Okay, so it'll be 2 pi times the frequency, 1 over 4 pi. Okay, so that is half, or 0.5 radians per second. Now we're going to look at acceleration of a uniform circular motion. We're going to look at acceleration of a uniform circular motion. Uniform circular motion. Now the question is, in this kind of motion, the particle is moving with a constant speed. Okay, so the speed is a constant everywhere. Okay, so the question is it an accelerated motion? Okay, remember velocity has two properties. It has magnitude and direction. And this kind of motion, even though the speed or the magnitude is constant, the direction is changing constantly. So this has acceleration due to change of direction. Okay, so even though the speed is constant, this is an accelerated motion because direction of the velocity is changing constantly. Okay, it is an accelerated motion, let's say uniform circular motion. Circular motion is an accelerated motion. An accelerated motion, even though the speed is constant, even though the speed is constant, because direction is changing constantly, because direction of the velocity is changing constantly. That's why it is an accelerated motion. We have acceleration due to change of direction. Velocity has both magnitude and direction, so you can change it either by changing the direction or changing the magnitude. So in this case, even though the magnitude is constant, the direction is changing constantly. And so because of the change of direction of velocity, this is accelerated motion. The acceleration due to change of direction is called centripetal acceleration. Okay, acceleration due to change of direction is called centripetal, which means center seeking acceleration, and we're going to use AC represented. Okay, all right, so we're going to try to obtain expression for this kind of acceleration qualitatively. We're going to do it quantitatively in a later chapter, but over here we're going to do it qualitatively using geometry. Okay, suppose let's say we have a particle moving in the following circular paths. Okay, in the following circular paths. Now suppose this is a velocity at this point. Okay, after a time interval delta t, it has the same magnitude, but we have changed its direction like this. Okay, and then let's say the center over here, and this is over here, and this distance over here would be arc lengths covered during this time interval. Okay, so this one is the arc length, and you've got the initial velocity and the final velocity. So to remember, acceleration is delta v by delta t. Okay, so the velocity has changed from here to here. So to find the difference, we got to connect both vectors tail to head like this. Okay, so this over here would be delta v. Okay, and if you use the scale, if you bring this vector over here, the direction of the acceleration will always be toward this the center. Okay, this would be delta v, and that would be directed toward the center. All right, if you use a scale, maybe let me write another one over here with both of them connected. So you've got like this. So let's say this is the velocity over here, and then after some time it will be inclined over here, but if you bring it over here, it will be something like this, okay? It will be something like this, and this will be delta V. If you use a scale, you'll find out that this is always directed towards the center, okay? So we have delta V always directed towards the center. And acceleration has the direction of delta V, okay? So that tells you centripetal acceleration is always directed towards the center. If you use the scale, you'll find out that this delta V, which is the direction of centripetal acceleration, is always directed to the center. So we have centripetal acceleration. Centripetal acceleration is always directed towards the center, directed towards the center. So if you take at this point, the direction will be this way. If you take this point, the direction will be this way, and so on. At any point, will always be directed towards the center. Okay. Now let's try to obtain the expression for centripetal acceleration in terms of speed. Okay. So we're going to look at these two triangles. We've got these two triangles, which is radius, and then we've got this angle over here. Okay. So we're going to look at these triangles. So in this case, we have the arc length is delta S, and then you've got the radius for the inner triangle. You've got radius, and this one is arc length delta S. And then we have the velocity changing direction. You got this one first, and then you got this one. So you've got this is delta V, this is V, this is V. Okay. Now these two triangles are similar. Okay. These triangles are approximately 90 degrees. We're talking about very time intervals. Okay. Or you see the radius and the velocity rotate by the same angle, so these triangles are equal. So these triangles are similar. All right. If two triangles are similar, it follows that corresponding sides are proportional. So if you take the ratio between these two, it should be equal to the ratio between the speed and the radius. So since these two triangles are similar, since these two triangles are similar, we have the following relationship. The ratio between corresponding sides is a constant. So you've got, you take the ratio between delta V and delta S, this to this, should be equal to the ratio between the speed and the radius. Okay, so let's take delta S to the other side. We have delta V equals V over R times delta T. Now if you remember, acceleration is change in velocity divided by time. Okay, so we're going to do that to both sides. V over R, this is S, I'm sorry, and then we've got delta S divided by delta T. So you see, this is distance divided by time, it's speed. So you've got the following relationship. So the centripetal acceleration is V over R times this V over here, or V squared divided by R. Okay, so the magnitude of centripetal acceleration is proportional to the square of the speed, and it's equal to the square of the speed divided by the radius. Okay, so this is an expression for the centripetal acceleration in terms of speed, and we've seen that the direction is always towards the center. Okay, so its magnitude is proportional to the square of the speed, and its direction is always towards the center. So that's how we calculate centripetal acceleration. Okay, now we're going to look at a general circular motion, a case where both the magnitude and the direction of the particle are changing. That is the case where the speed is also changing in addition to the direction. Okay, so let's look at general circular motion, or non-uniform circular motion, let's say. Non-uniform circular motion. Okay, This means speed is also changing in addition to direction. Speed changing in addition to direction. So we have two kinds of accelerations over here. We have acceleration due to change of direction, which we already saw in the previous section. It's called centripetal acceleration. And in this case, we have also acceleration due to change of speed. So there are two kinds of accelerations in this case. Two kinds of accelerations. One of them is acceleration due to change of direction. Acceleration due to change of direction. We have already seen this type of acceleration. It's called centripetal acceleration, and it's equal to the square root of speed divided by the radius, and it's directed always toward the center. Okay, so this kind of acceleration directed towards the center, as we saw in the previous section, also equal to b squared divided by the radius. Okay, the second type of acceleration is acceleration due to change of speed. This is acceleration due to change of speed. We call this type of acceleration tangential acceleration. Tangential acceleration. Okay, and we're going to represent it by AT, tangential acceleration AT. Okay, all right, so let's look at the direction of this kind of acceleration. So if you change the speed without changing the direction, it's obviously going to be tangent to the circle. Okay, so tangential acceleration is always tangent to the circular direction. So direction of this kind of acceleration is tangent to the circle at any point. Its direction is tangent to the circle at any point. That's why we call it tangential acceleration. Okay, it's tangent to the circle at any point. All right, so now let's look at both accelerations. This is tangential acceleration, and radial acceleration is always toward the center. Okay, and if you remember your geometry, the radius and the line tangent to the circle are perpendicular to each other. So it follows that tangential acceleration and centripetal acceleration are always perpendicular to each other. Okay, so tangential acceleration, tangential and centripetal acceleration are always perpendicular to each other. Acceleration are always perpendicular to each other. Perpendicular to each other. Okay, so we have this relationship. The vector tangential acceleration is perpendicular to the vector centripetal acceleration. Okay, so how do you find the net acceleration? They're perpendicular to each other. Okay, let's say this is our AC, let's say it's our tangential acceleration. You see the circle is going somewhere like this, so the net acceleration is over here. Okay, this is the net acceleration. Let's call it A net. As you can see, if this is AT, this is AC, this is AC, this is 90 degree over here, So we can use Pythagorean theorem to get the net acceleration. So the net acceleration is simply from Pythagoras theorem the square root of the square of the centripetal acceleration plus the square of the tangential acceleration. Okay, so that's how we calculate the net acceleration of a non-uniform circular motion. We have two kinds of accelerations. Tangential acceleration and centripetal acceleration. They're perpendicular to each other, so we can obtain the magnitude of the net acceleration using Pythagorean theorem, which is the square root of the square of centripetal acceleration and tangential acceleration. Okay, now let's look at an example. Okay, let's say the speed of a particle revolving in a circular path, let's say of 2 meters. Let's say change its speed from, let's say, 5 meters per second to maybe 15 meters per second, let's say in 5 seconds uniformly. Okay, so the question is, by the time its speed is 15 meters per second, calculate its net acceleration. Calculate its net acceleration. Okay, so we're looking for a net. Okay, that's question mark. But to get a net, we're going to need to calculate both the centripetal acceleration and the tangential acceleration. Okay, so we're asking for the net acceleration. This is 15 meters per second. So we calculate the centripetal acceleration from the square of the speed divided by the radius. Okay, we're told the speed is 15 meters per second and the radius is 2 meters. Okay, so the centripetal acceleration is 15 squared divided by 2. That is 225 divided by 2, which is 111.2.5. Okay, this is meter per second square. All right, that is the centripetal acceleration. Now let's calculate the tangential acceleration. So we're told it's changing at a constant rate from 5 meters per second to 15 meters per second. So we can say, we can use equations of a uniformly accelerated motion. That is tangential acceleration equals del change in speed divided by time, which is b final minus b initial divided by the time taken. Okay, so the speed changes from an initial of 5 to 15 in 5 seconds. Okay, so we have is our v initial speed is 5 meters per second, our v final is 15 meters per second, and the time taken for the change is 5 seconds. Okay, so from this information we calculate the tangential acceleration. So that is 15 minus 5 divided by 5. That's 10 over 5. That's 2 meters per second square. Okay, now we calculate the magnitude of the net acceleration. It is square root of ac squared plus at squared. Okay, will be the square root of this 112.5 squared plus 2 squared. So it'll still be approximately equal to this one. So that'll be the net acceleration. Okay. All right. So summarizing, in a non-uniform circular motion, we have two kinds of accelerations: acceleration due to change of direction and acceleration due to change of speed. The acceleration due to change of speed is called tangential acceleration. Acceleration due to change of direction is called centripetal acceleration, and these two accelerations are perpendicular to each other, so the net acceleration can be obtained from Pythagorean theorem. In this section, we're going to consider relative velocity. Relative velocity. Velocity is not absolute. It depends on the reference frame from which the velocity is measured. For example, let's say you have a boat moving in a river. You can talk about its velocity with respect to the river, or you can talk about its velocity with respect to the ground. So the velocity depends on what reference frame you decided to use. It's not absolute. It's a reference frame dependent quantity. Okay. For example, let's say we have car A, let's say going at 20 meters per second, let's say this way, and then you've got car B moving at 30 meters per second in this direction. So these are, of course, velocities with respect to the ground. This is velocity with respect to the ground. But if you're asked the velocity of B with respect to A, you see B is going away from A at a speed of 10 meters per second, which is the difference between 30 and 50. So its velocity with respect to A would be 10. Let's say both of them have the same speed, 20. The speed of B with respect to A would actually be 0. Okay? And let's say A is going in this direction with a speed of 20 meters per second. And let's say B is still going with 30 meters per second in this direction. And if you're asked what the velocity of B with respect to A, let's see, this one's 30 meters per second this way, 20 meters per second this way. So the velocity of B with respect to A would be 50 meters per second. Okay, so let's try to do it quantitatively. Let's say we have, first we're going to consider one-dimensional case. Okay, let's consider one-dimensional case. That is motion in a straight line, and then we're going to generalize to 2 dimensions. Okay, suppose, let's say this is one reference frame. Let's say it's reference frame A. We have another reference frame over here, reference frame B, and then we're talking about the velocity of this particle C. Okay, now let's look at the position vectors. The position vector of C with respect to A is this one over here. Okay, so there's only one direction, so we're going to talk about components. So this one is the position of C with respect to A, and this one over here is the position of B with respect to A. Now you see, this one over here is the position of C with respect to B. This is the position of C with respect to B. So very easily you can see that the sum of these two equals this one. So you can say that the position of C with respect to A equals the position of B with respect to A plus the position of C with respect to B. Okay, so we have this equation: xCA, the position of C with respect to A, equals the position of B with respect to A plus the position of C with respect to B. Okay, let's say we're trying to find out this, the position of C with respect to B. Then we have the following: the position of C with respect to B is the position of C with respect to A minus the position of B with respect to A. Okay, now let's say all this are moving. Okay, so let's find the velocities. The velocity is the derivative with respect to time. Okay, so we have the derivative of x, position of C with respect to B with respect to time, equals the derivative of the position of c with respect to a with respect to time minus the derivative of the position of b with respect to a with respect to time. Okay, so these are velocities. This term over here is the velocity of c with respect to b. That equals the velocity of c with respect to a minus the velocity of b with respect to a. Okay, so you see the velocity of c with respect to b is simply the velocity of c with respect to a minus the velocity of b with respect to a. Okay, so we have this formula for a one-dimensional case. Okay, so as I said before, this is a one-dimensional problem, so these are components, so they could be positive or negative. Right will be positive, left will be negative. Okay, let's consider an example of this. Let's say example, let's say car A is moving, let's say, towards west with, let's say, a speed of 30 meters per second, of course with respect to the ground, with respect to the ground. Okay, and then let's say car B is moving, let's say, towards east with a speed of, let's say, 40 meters per second, of course with respect to the ground, with respect to the ground. Okay, so in this case we have the ground involved, we have car A involved, we have car B. Okay, so let's write what we know. What we know is the speed of car A with respect to the ground is 30 meters per second towards west. Okay, so the speed of A with respect to the ground is west, so we're going to put negative, is negative 30 meters per second. And then also the car of B with respect to the ground. The car of B with respect to the ground is moving towards east with a speed of 40 meters per second. This is east, so it's going to be positive, okay? 40 meters per second. Okay? The question is, what is the velocity of A with respect to B? Okay, so we want to find the velocity of A with respect to B, question mark. Okay, so if you follow this formula over here, you see CB, C with respect to A, B with respect to A. Okay, so the VAB according to that formula equals VA with respect to the ground minus speed of B with respect to the ground. Okay, following that formula. So you can do it intuitively. I'm just trying to show you an application of this formula. So the speed of A with respect to G is negative 30 meters per second. Okay, and the velocity of B with respect to the ground is 40 meters per second minus 40 meters per second. So you see, this is negative 70 meters per second. So car A with respect to B is going at 70 meters per second west. This means 70 meters per second west. So you know what this means? You've got this one going with the speed of 30 this way, and this one going the speed of 40 this way. The speed is A. So you see, this car is going 30 plus 40 away from this car per second. That's what this means, right? Okay, now we're going to generalize to two dimensions. So basically it means we're going to use two-dimensional position vectors. So we're going to use, the only difference is we're going to use two-dimensional position vectors. Dimensional position vectors. This is motion in a plane. Okay, so suppose we have the following coordinate systems. Let's say this is our reference frame A. Let's say this is our reference frame B, and let's say we have this particle over here, particle C. Okay, so its position vector with respect to A is this position vector over here. So this is the position vector of C with respect to A. And the position of this reference frame with respect to A is this one. So this would be the position vector of B with respect to A. This position vector over here is a position vector of C with respect to B. So we have position vector of C with respect to B. Okay? Now you see, you remember how to add vectors? If these two vectors are joined tail to head, then the vector connecting the tail of the first vector to the head of the last vector is the sum vector. So from this triangle, we can conclude this equation. The position vector of C with respect to A equals the position vector of B with respect to A plus the position vector of C with respect to B. Okay? And if you're interested in this one, position vector of C with respect to B, then we have position vector of C with respect to B equals position vector of C with respect to A minus the position vector of B with respect to A. Okay? Now to find the velocities, we take the derivative of this equation. So you've got the derivative of position vector with respect to B with respect to time equals the derivative of position vector of C with respect to A with respect to time minus the derivative of the position vector of B with respect to A with respect to time. Okay, so these are velocities. So this one is the velocity of C with respect to B. This is the velocity of C with respect to A, and this is the velocity of B with respect to A. Okay, so this is the two-dimensional equivalent of the relationship between the velocities. Okay, now let me note something before I proceed. If this is VCB, then what is VBC? This implies the velocity of B with respect to C would be the velocity of B with respect to A minus the velocity of C with respect to A. So you see, this is just negatives of each other. So it follows that the velocity of C with respect to B is the negative of the velocity of B with respect to C. So if you reverse the order, they will be negatives of each other. Okay. Okay. Now let's consider an example. Let's say car A is going with, let's say, a speed of 20 meters per second, let's say making an angle, let's say of maybe 37 degree, let's say west of north. Okay, car B, let's say, is going west with a speed of, let's say, 10 meters per second toward this west. These are, of course, velocities with respect to the ground. The question is, calculate the velocity of A with respect to B with respect to B. Okay, so let's try to review now. The velocity of A with respect to the ground is 20 degree, making an angle of 37 degree west of north. Okay, so this velocity is like this. 37 degree west of north. This is north. So this is the velocity, and this is 37 degrees. Okay, and so this is the velocity of A. The velocity of B is this way, and it is 10 meters per second. Okay, so this is with respect to the ground. This is BB with respect to the ground. Okay, so that's what we have. The velocity of car A with respect to the ground is this one, 20 meters per second, 37 degree west of north. Okay, so we're going to write that in ij notation. This is a vector, so the magnitude is 20, the direction is 90 plus 37, which is 127 degrees. Okay, so let's write in terms of components. So you've got VAG equals 20 cosine of 127 in the I direction plus 20 the sine of 137 in the J direction. Okay, so this would be 20 times 0.6. Okay, so it's going to be about 12 in the negative I direction. Okay, I direction, and this would be positive 16 in the J direction. Sine of this would be 0.8. The cosines will be negative 0.6. Okay, so this is the velocity of A with respect to G, that's meters per second. How about velocity of B with respect to the ground? It is 10 meters per second west. Okay, so the magnitude of BG is 10 and the direction is 180 degrees. Okay, that's west. So we can write in ij notation. So this vector VG equals 10 cosine of 180 degree in the I direction plus 10 sine of 180 degree in the J direction. Okay, so this is negative 10 in the I direction plus 0 in the J direction. Okay, it's going west. Okay, so we have this velocities, and we're trying to find velocity of A with respect to B. Okay, so we're looking at the velocity of A with respect to B question mark. Now the velocity of A with respect to B is the velocity of A with respect to the ground minus the velocity of B with respect to the ground. Okay, so we just plug in these numbers. The velocity of A with respect to G is negative 12 in the I direction plus 16 in the J direction, minus the velocity of B with respect to the ground is negative 10 in the I direction. Alright, that's it. So for the I part, you've got negative 12 plus 10, that's negative 2. Negative 2 in the I direction, and then you've got plus 16 in the J direction. So this is the velocity with respect to the ground, VAB. Okay, how about if you want to find VBA? Okay, VBA will be simply the negative of VAB. Okay, that will be the negative of negative 2 in the I plus 16 in the J meters per second, and that would be 2 in the I minus 16 in the J meters per second. Okay, another example. Let's consider, let's say we have a river that goes downward. The river, let's say, is going downward with the speed of, let's say, maybe 5 meters per second. Okay, so a river is moving toward the south, let's say. South with a speed of, let's say, 5 meters per second. 5 meters per second. Now, if a boat is going towards east at a speed of, let's say, maybe 4 meters per second, okay, with respect to the river, okay. The question is, calculate the velocity of the boat, with respect to the ground, okay. So the river is going the negative j direction. That is the velocity of the river with respect to the ground. So first, let me say I'm going to use R for river, I'm going to use B for boat, I'm going to use G for ground. Okay, so that's what we know. For the river, that is the velocity of the river with respect to the ground is towards south, so that is -5 in the j, okay. And then we're also given the velocity of the boat with respect to the river, okay. That is 4 towards east, okay. That's 4 in the I. So the question is to find the velocity of boat with respect to the ground, okay, question mark. All right, so using the general formula, we can write VBG is VPA with respect to the river minus the velocity of the ground with respect to the river, okay. So we have this one, V boat with respect to the river is this one over here. Now we have the velocity of river with respect to the ground, but the velocity of ground with respect to the river, okay. So we can modify this one, boat with respect to R minus, this is the negative of this one, V of river with respect to the ground, okay. So you've got, this is the velocity of boat with respect to the river plus the velocity of river with respect to the ground, okay. So we have the velocity of boat with respect to river is 4 in the I direction, and the velocity of river with respect to the ground is -5 in the j direction, okay. So that's it. That is the velocity of boat with respect to the ground. All right, so if you want to find the magnitude, this is a vector. If you want the magnitude, it'll be VG square root of 4 squared plus 5 squared, which is 16 plus 25, that's 41 meters per second. And the direction would be tan inverse of the y divided by 4, okay. So you see what this means is you got the river pushing down this way and the boat is going this way. So for somebody who's looking from the ground, it looks like the boat is going this way, okay. Basically the sum of these two vectors over here, all right.